Yeah, but I'll bring them to lab. I don't have them on my immediate person. All right, let's get started. So I at least wanted to touch base because a student had shared this article, so talking about potentially some of the impacts. So we were talking about like last chapter, right, with the wind and maybe putting offshore windmills, or that was something people have been exploring. And so this article is kind of interesting. And so, of course, you know, it's just a short, at least relatively speaking, study. But they were saying that at least they think that they're whale deaths. And then, of course, officially they're saying no. But, you know, who knows, right? Like, you always have to be studying. You always have to look at what your impact may be. Let's see. Yeah, so they were saying that apparently these turbines emit a lot of noise and maybe even like some sort of radiation. So they mentioned this, that there's operation noise, electromagnetic fields, and thermal radiation. So don't know how that's affecting the wildlife. And what was interesting, I'm trying to find it in the article. Yeah, so remember, I mentioned it in class, and they said it again because the idea was, oh, this is supposed to be great. We're going to put these wind turbines out there. And right, they even said it right here that so the large underwater platforms are supposed to get colonized by the small marine life, and then that's supposed to, of course, you know, attract the larger whales and other big fish. But of course, they're saying, well, they didn't really maybe take into account all the operation noise, which could actually be driving the whales away or messing them up or, you know, causing something. So always interesting. And of course, this is always a huge issue with like science, is like who's backing the research. And, you know, that's always not to go down a rabbit hole, but that's always an issue. It's like who's actually paying for the research. And, you know, you have to sometimes see what those conclusions are.
Because there's a ton of history of like, you know, food industries funding their own surveys and kind of having it tilted in their
Exactly, yeah.
direction. That's the kind of the terrible thing about statistics, is it can be the same numbers but presented in a way where, you know, it's presented in a positive versus a negative light.
Yeah, and that's why like I keep encouraging y'all to take statistics, because you got to even understand like what is statistically significant, because you can, you know, look at these numbers and oh my gosh, there's a difference, but maybe it doesn't even matter, you know, plus or minus, whatever. So that's always, yeah, you always got to look at it.
It's a fun class. It's a lot of work, but it was a fun class.
Yeah, like highly recommend take statistics. It's good for you. I'll let you vouch for it. But I mean, I enjoyed statistics taking it. It was easier than calculus for sure. So. Yeah, and it's also just like with anything, and I wanted to save this topic for later, but I'll bring an article once we get more into like sea organisms. But like there's a law off of the West Coast because there was like some sea urchins were getting overhunted, and they're like no more harvesting them. And then next thing you know, all the sea urchins like took over and it became an invasion. So it's like we always have to be careful with our policies, you know, not to go from one extreme to the other. And then also, you know, obviously we can't predict the effects of everything. Like another rabbit hole is plastic, right? We invented plastic, but now we have this issue of microplastics and plastics in our water and plastic everywhere. Like in hindsight, we maybe should have never invented plastic, but.
Well, we're just really good at overcorrecting.
Yeah.
You can never find the middle ground. It's like when they introduce an invasive species to deal with the pest.
Oh, yeah.
And that invasive species becomes the pest, and then you have to bring in another predator. Like Florida's notorious for this. I mean, we did it with bullfrogs here in Oregon.
Oh, I didn't.
Yeah, we did bullfrogs to deal with something, and now we have this problem with bullfrogs eating all of the native wildlife at like these ponds and lakes and stuff. And so now you can fly fish for frogs, and it's like a no bag limit. It's the weirdest thing.
Yeah, I can't say I've eaten frog legs personally. Well, yeah. Anyways, well, always good to keep in mind though, right? So again, get involved with your local issues. That's ultimately what it's about. All right, so now we're switching over, or moving on to chapter 7. And so chapter 7, now we're looking at more of the ocean currents. So 6, we look more at wind, and of course we'll see how these are related. And so just broad definitions, so ocean currents are just moving loops of water. And so each ocean basin has its own circulation pattern, which you kind of got a taste of looking at in the last lab. And of course, currents also redistribute the global heat, so we've kind of touched on this before. And so we'll look at, so this is a new term, thermohaline circulation. So this is, we'll talk about this at the end. So this is going to be a deep current versus some of the like surface currents that we'll talk about. And of course, how currents affect marine life and maybe sources of energy. All right, so we'll look at our, start with surface versus deep currents. And so surface currents are more wind-driven, and they are primarily horizontal. But of course, what do you remember about the wind and how it affects the surface? Or why is it called surface currents even? So yeah, I mean, they are on the surface, right? But, you know, what, do we want to say anything more about that? So,
Well, it's gonna be different than deeper down.
so that too.
Vastly different. The speeds can be different, the temperatures can be.
So, yeah, so I like what you're saying. So right, in summary, then we have a lot of different effects, right? Because you have your wind with your surface current, but then you mentioned, well, then you have your deep currents are affected by density, temperature, salinity.
Because sometimes the deeper currents are much slower than the ones on the surface. You see that a lot, like especially in rivers and such.
Let's see, I'm trying to summarize all that you said. So that's good. So deep currents, let's just say, all right, so can be different. So that was, I think, the main point you were getting at. So you can have, right, different action, different directions, different speeds.
You can also go in opposite directions too.
Yeah, so let's add that. So opposite directions. And we'll kind of look at this on the global map. So different speeds, that's good summary. And so what I was trying to go for, you know, I like numbers. So only 2% of your wind energy gets transferred down into your ocean. And so again, wind, right, just more surface, like you were saying, so surface currents. So a lot of that wind energy gets lost. And of course, right, you could blow on your like little drink and just kind of imagine the effects of the wind. And so excellent, you were touching on the deep currents, and you kind of saw that with your density experiment and how those rotate around. And of course, we'll talk more about the deep currents. And so of course, note, right, they have both vertical and horizontal motion on the deep currents, while the surface is mainly, right, just horizontal. But those deep currents, right, that's what really churns the difference in nutrients. So maybe let's add that.
Is that 2% going to be important to remember?
I probably won't quiz you on that. I haven't decided. Again, you guys can help me try to figure out how to make my exam. I'm kind of thinking about doing like map interpretation, though, for a lot of it. So add nutrients usually. And right, we're thinking of like oxygen as well for the deep currents. And so how do they track currents? So buoys, so we looked at that. And so, right, those buoys, they can just track them over time. They,
Somewhere that they've done it with like, schooling fish, because fish will take like the, I don't know if this is true or not, I read it, in I think like a Trout Unlimited, and they were talking about how they track, currents with schooling fish, because fish will take the least, resistant path.
yeah.
So, they'll jump into so they'll track, they'll tag a couple of like salmon or something, and they'll watch them where they go.
Excellent. So we got buoys, fish, and of course your book kind of shows other devices. So they have this propeller flow meter that can be dragged along. And so looking at this map, so now what this map is showing us is, so this is just our sea surface height. And so yellow is going to be average, and so our red is kind of higher. So what does this tell us? What kind of motion are we going for with this? And what does it kind of remind us of as well? So I guess I'm trying to say, like, we can look at this map, right? And what is it telling us, first of all? So we're looking at different heights, but why is that?
It's telling us like where sea level is in different spots?
Yeah, so that's what it's telling us. But then what other information? Because they're implying something that this starts telling us some information about our currents.
The highest portions are within the Tropic of Cancer and Capricorn possibly.
The speed.
And so I like what you said. So you identified these highest portions. And so think about this, like, what if this was a mountain instead? And what is that telling us? So how does, like, water flow?
Yeah.
So it flows down. So, right, this is just our first basic look then of what water is flowing, like which direction. So I was kind of thinking of relating it to a topography map. I can't spell anything. Right, so the key point here is just like a topography map. You can see, right, what's higher, what's lower. So you're kind of seeing, right, the difference in elevation, but of our sea. And so, of course, gravity dictates how water flows. So this overview is just like our basic, where's water flowing from? So like you were noticing, okay, our highest areas are in the equator. So they're going to be tending to start there, right, and then take that warm water out. And so we'll see that in the next page. So that's all that we're trying to get at here. And so if we zoom in too, so we can start looking at these little arrows. And so these arrows also kind of tell us how, again, our topography at least starts giving us an idea of our current flow. So you can kind of see that. Again, it's always kind of flowing out and away from these higher areas. And then, of course, we can see it floats along. Well, it's also kind of, spiraling. And so we'll look at that, right, as we go through this book, but we'll see, right, so it can make little spirals and like areas of depression, of cooler waters. So there's different things going on. So you're right? So it's not the complete picture, right? Gravity is just a part of this picture. So let's keep looking. And so, of course, other ways that they can measure deep currents and track things are chemical tracers. So these are more unintentional. So do people know what tritium is? So tritium, so hydrogen, 1H, right? This is like your standard, we would say, isotope of hydrogen. And so 1H meaning it has a mass of 1, so it has 1 proton, no neutrons. 2H, this is called deuterium, and affectionately known as heavy water. And so now this would have 1 neutron. So tritium is 3H, so it's just even heavier than deuterium, so 1 proton, 2 neutrons. You don't need to know the proton-neutron stuff. But basically, this is just radioactive, and so it's relatively short-lived half-life, so you can help follow that, so that's why it's useful as a chemical tracer. And then chlorofluorocarbons, so right, these are the CFLs that were in like refrigerators, and so you can track those as well. And then of course, right, measuring the temperature and the salinity, so they mention how they'll put down these Argos. So these are little free drifting floats, and then they go down, sink down to programmed depths, measure salinity, temperature, other information, and just try to track that. And so you can see, right, all the little floats, all the little data points. And so they dive 2,000 meters deep and get you the sample. All right, so looking at our surface currents, so they occur above the pycnocline in our ocean depth. So again, surface just at the top. And so only about 10% of the ocean water is affected by this. Again, you know, you guys have already determined that your deep currents drive a lot of your motion. And so like I had mentioned, only 2% of that wind energy is transferred. So of course, right, the effect of the wind is a lot less. And so the surface currents are going to be a slower speed than the wind. That makes sense. And of course, right, they generally follow the Earth's wind belt pattern, but again, we'll look into issues with that. So of course, right, oh, sorry.
So is this the energy? That's, so I was kind of following along like the principal cost notes. One of them is what is the energy source of surface currents? Is that what the energy source is?
Yeah, so it would just be like the wind. Yeah, so it's very small. So let's see. And of course, right, the problem though, of course, as it follows the wind is it's also going to run into continents. And obviously that's going to affect the flow, so we're going to look at that. And of course, it could run into other currents. Are we ready? All right, so here we were kind of looking at our trade winds before, so we can first kind of orient ourselves with our trade winds. So let's just study this graph. So we have our trade winds, so our light green arrows. Oh, those aren't our trade winds. So these are our trade winds. So we mentioned those on Tuesday. So trade winds, right, trade winds. So we mentioned the Coriolis effect. I shouldn't have used green. So we have that. And then, of course, our westerlies going in the opposite direction. So we mentioned the wind. We could always pop back to the wind section. And so, right, we have our air motions. We can kind of see that. And so, where's in blue? So blue is our ocean surface currents. So now we're getting, right, some of that rotation. And of course, right, we have continents. So this is what causes it to take a different pattern. So if there are no continents, right, it would just blow across the Earth. But with these continents, that stops it and kind of helps create this loop motion. And so we have a similar effect in the southern hemisphere, of course. And so we're going counterclockwise here. So notice, right, these are in opposite directions. Part of that from the Coriolis effects. And so, of course, things that affect our currents as we look at them. So obviously the continents are big masses in the way. And so we'll look at those, how those influence each ocean basin. And obviously we've mentioned gravity. We'll touch on friction a little bit more, but of course that's a big factor. You know, just physically think about the water moving through and friction with itself. And then obviously we can't forget the Coriolis effect. So, you know, another thing you're appreciating hopefully is a lot of factors, a lot of things to consider when trying to model this and trying to understand exactly how our currents work.
How does that affect the currents?
Which one? Sorry.
Coriolis effect.
So the Coriolis effect, right, that causes it. So we'll look at it in detail, but right, it helps cause that circular motion, but then we'll kind of see this unevenness in like the west intensification, but we'll get there.
Okay.
So we'll save that. And so now we have our gyres. And so what's our basic definition of a gyre again? Yeah, so it's just a large circular loop. So large circular loop of water. And so really all we're doing is, so we're looking at this main ocean movement, and now we're just breaking it down, kind of defining it more, and looking at these individual gyres as they define them. And so we have different gyres here. So you have your main ones, and so they have other names, but we would just look at them. And so I might expect to do something like this on an exam if I like made you label the gyres. I think that's pretty simple. So right, we have our North Pacific subtropical gyre. And so notice, right, the Pacific and the Atlantic both have two gyres. So that's kind of from the Coriolis effect as well, right? So you have one on your northern hemisphere with your circular motion here, then one on your southern hemisphere, so of course going in opposite directions. We can go back right to the big picture map if we need. Okay, so North America is going clockwise here, and so now we're kind of piecing, right? So these are all the pieces of that big circular motion, and so we'll look right at the individual currents that make up each gyre. So then in the Pacific Ocean, on the southern hemisphere, we have our South Pacific subtropical gyre. And again, we can see the currents that comprise it. And so these are the ones labeled 1, 2, 3, 4, 5. So those are your main 5 ones. And so, of course, right, you have your North Atlantic one. So going, again, in our clockwise motion. So the Gulf Stream is a big component of that, so that's pretty famous. And then, of course, the Canary comes down, meets back up with our north equatorial current. So look at the south. So again, opposite motion, right? So now this is counterclockwise. So going. And so, again, this is also from the Coriolis effect. So we kind of mentioned both the trade winds, right? So the trade winds are going across, but then with our Coriolis effect, so it takes the warm water from our equator and sends it up, or sends it right away. So in the northern hemisphere, it goes up. Southern hemisphere, so it goes down. So looking at that with the Brazil current. And of course, again, this one's now part of the South Atlantic subtropical gyre. So I think that's probably fair game for potential exam questions. And so Now, we also have our Indian Ocean subtropical gyre, and it has interesting features as well. So it has monsoons, which dominate a lot of the current patterns and the weathering patterns. And so, and this one's more in like the southern hemisphere, so you can see it. So here's the equator, 0 degrees, so you can orient yourself there. And so again, it's going in your counterclockwise movement in your southern hemisphere. And then we can also look at our subpolar gyres. So these are more defined broadly, so you can see they occur around the 60. I'm trying to find the 60. So the 60 is up here, I believe. It would be nice if they had more markings. So I'm not sure with that one. Where's our other subpolar? So again, around right the 60 degrees north or south latitude. And so those are just more broadly named, you know, subpolar gyres, so all those on the extremes. Let's see, what else do we want to say? All right, so now we have basically different definitions of all these. So now we can kind of define all our equatorial currents and our different currents. So equatorial currents are north or travel westward, so they can be right north or south, so we can look. And again, we were looking at this with the winds, so they just go across here. So right, our north equatorial current, our south equatorial current. And then what's this counter current kind of caused by? What also happens here? Or any comments about this counter current too? So not necessarily, but so what's kind of going on too? So that would have some effect. So right, we have our north equatorial currents going this way, south equatorial current, and then yeah, they're kind of hitting these islands. So what might happen? And we could even think back, right? Think back to our really broad picture here. Right, so this is where our currents are going. So they're like crashing on these islands. So we get a counter current. You can even kind of see some of that counter current maybe in these arrows. But what could be happening? Yeah, that's basically. So right, and we go back to this map, and that tells us a picture of that, right? So you have all these currents going in this direction. And so looking at this picture, right, it creates a higher area just physically, right? There's just physically more water. So then kind of like what you're thinking, yeah, there's going to be a little stream then running back. So, you know, just thinking about a mountain, it all ends up on top, and now gravity is going to bring that counter current back down. So there's the counter current, and we'll see some of that. So some of this motion, so again, right at your equator, your currents are taking everything away from your equator, and so we'll look later in this chapter, but that also creates, right, upswelling, so bringing up nutrients to the equator, so that's really good. So that helps keep that in motion. Let's see. And so let's look at our western boundary currents, but I want to skip ahead back to your question. And so let's look at, so just basic definition of our western boundary currents is they're going to tend to be on the west, and they're going to be warm waters, so western edge of ocean basins. but let's see, we'll skip. There we go. This is what I was looking for. So we'll come back to the Ekman. But basically, this is a good picture of what's going on. So, right, we have our rotation, just our general circular rotation, right, from our currents. But then, so we were asking about the Coriolis effect and how this, again, affects the currents. And so what happens, right, your Earth is rotating. This is flowing. And so looking at this map, and I like this picture because it gives you a good sense of what's going on. And so look at the lines here, how they're a lot closer together, right, because of the Coriolis effect. And so that means a lot of your western boundary currents are going to be extremely fast and narrow. And so we can look at that on a map. So this is why this is. So again, your Coriolis effect makes it so where this side is more intense as it spreads, right, you're moving across. So then your west side is always more intense. It's always faster. And then on the east side, your currents kind of get more diffuse, and it gets physically harder to track those currents. And so your book mentions that. And so here is the effect. So it's called the western intensification. And again, kind of thinking of the hill too, so everything is kind of getting squished and pushed physically on one side. And so again, that makes those currents faster, narrower, deeper, and warmer. So let's go back to some of our western boundary currents, and we can identify that, yes, they do exhibit that. So what are some western boundary currents? What would be some? You said California current? Yeah, so that would be an eastern. This would be an eastern current.
Okay, that confuses me.
Yeah, so the Kuroshio would be a western boundary. So it's just west-east. Yeah.
Oh, okay.
So, yeah, so relatively speaking, right, this is west, this is east, because you're just looking at that specific gyre then.
Okay, so we're just looking at that, okay.
Yeah, so you're focusing, so like focusing on this gyre then. So yeah, just like you said, you identified the Kuroshio then would be our western boundary current for this one. And so it is warm, right, from our map. So it's warm. It's probably moving pretty fast. I'm trying to find. There we go. I knew I just needed to find the right chart. Oops. So back to this. So this is a good summary. So it tells us, right, so Gulf Stream, Brazil, Kuroshio. So those are all western boundary currents. And so, right, they all have this. They're narrow, they're fast, they're large. And so again, we can just identify that on the map. So right, your Gulf Stream, so looking, now we're focusing at our North Atlantic subtropical gyre. So again, the west side, this is going to be our Gulf Stream. It has that western intensification. So we all know, right, that it's pretty fast. There was that, if you read the textbook, there was like a cute little story about how back in the day, Ben Franklin and his buddies were like trying to figure out why the mail moves so fast following the Gulf Stream. So they were trying to figure that out, and that's how they mapped the Gulf Stream. So again, fast-moving current, and on the west side versus, right, the Canary, so that would be an eastern boundary current.
So the eastern ones are going to be slower, shallower, and wider?
Yeah. Yeah, and so it follows, so even then, so now looking right on the southern hemisphere, it's still west to east, so it still follows that pattern, right? So west, so this Brazil current is going to have that western effect. So and it's warm, it's fast moving, and it's just going the opposite direction, right? So this is going, again, clockwise, this is going counterclockwise, but the point is they're both moving away from the equator, right? So making their spirals. So this is our western one. And then, of course, I can't read that, Benguela current, so that's our eastern current again. So we can identify that. And right, so same thing, so we notice this, so our western boundary current for this gyre here, again, it's fast, it's red, versus our eastern boundary, our Peru here, that's slower.
That's specifically because of the speed of, or the spin of the Earth, right?
Yeah, so the Coriolis effect, so that has like a big influence, but then also, right, going from warm waters to cool waters, so that's the first movement, and then, yeah, the Coriolis effect makes it turn more. And then, of course, the continents are also in the way, which they tend to follow the continents, as you're seeing.
So, in summarizing, the Coriolis effect causes it to spin more?
Yeah, well, so you have, so let's maybe go back to this picture, right? So not only do you have rotation, right, but as your Earth rotates on the west side, yeah, it causes it to be more intense because you're kind of thinking of it as a wave, right? So as the Earth moves, the east side kind of gets more diffuse, while your west side, the currents smash up as you move, and they move like closer together. So yeah, the west side, it always has that effect, even in the southern
How come
hemisphere.
it doesn't do that to the east? I guess that's what I'm not understanding.
No, so in the east, it does the opposite, right?
So, I mean, how does it do the opposite if it's just?
Well, because maybe I have to get a globe, right? Because your Earth is rotating, so then as it rotates, it like spreads the currents out on the east side, right, from your winds and everything. Because you have, and it's also, so you, right, you have to look at your rotational center. So if you look at this graph here, so your center is offset because your Earth is always moving, essentially. So like this part, just think of it, if the Earth is moving, you started with like a, let's say a concentric circle, which I didn't draw very well. But then the Earth is moving, so it's almost like spreading these bands further apart, but then this shifts our center over and squashes these together.
Okay, so it's gonna be like inertia is gonna push
Yeah,
everything, and then on the other side is gonna be stretching it. Okay.
yeah. Yeah, so you have to think about, yeah, if you want to think about like the
So I'm just
inertia of
picturing,
everything.
like, you would take, like, my daughter has this toy where it's like a sponge attached to a, like a rope, and she gets it wet, and she spins it, and everything just kind of naturally kind of goes in all directions. So I
Yeah,
was just
so if you could like
curious.
spin it, but then also pull it, then you would get, all right, a spreading
Okay, so if she
effect.
spins it, it starts spinning herself, she should get the similar effect.
Yeah, or like spinning and dragging.
Okay.
I know, it might be hard to like simulate.
We'll keep her busy, so that's.
Yeah. Let me know how all those simulations turn out.
She's obsessed with this stuff, so she loves the sciences, so she's like super intense on like, I gotta figure this out.
You got to get her on all that centripetal motion and yeah, all that's good. All right. And so then our northern and southern boundary currents, so these are just kind of now what's left over in the middle. So kind of like our North Pacific current here. And so we have, right, northern boundary currents and for the northern, southern boundary currents for our southern hemisphere.
So is it just,
Oh, sorry.
kind of going over the notes again, things that can slow change or redirect the currents and just other currents, continents, and wind? Is that what
Yeah, wind and, well, we could also go into like the topography of the ocean itself can change the currents.
Okay,
Like
so
we
pretty much
mentioned with the
anything
countercurrent.
that causes obstructions.
Yeah, so any
Okay.
obstructions or like differences in elevation.
Okay.
Cause like rifts and stuff like that in the ocean make a difference too.
Yeah, so all that, yeah, so there's a
Because
lot.
in a current, if, like, for instance, if you have a couple rocks, you'll have it, it'll slow down right here, but in the center, it turns into like a jet. Because
Yeah.
of, it consolidates into a smaller stream. Okay.
Yeah, so we have, yeah, so again, a lot of factors, so not only taking into account your underwater topography, especially with deeper currents, but obviously the land masses. So yeah, touching on a lot of good ones. Let's see.
Would you consider temperature something that was slow?
Yeah, I mean, I would put it in there.
Maybe like the density?
Yeah, because we'll look at that too with the Gulf Stream, how that's kind of interesting, where it runs out of steam in some way. All right. Let's see, so other surface currents, so we kind of looked at these equatorial counter currents that we mentioned. And they're also apparently due to minimal Coriolis effect, but again, I would attribute this to our higher sea levels, so you guys saw that. And so then we also have our subpolar gyres, so these are, again, I think I already said that they're at the 60s approximately. And these are kind of interesting because they rotate opposite of our subtropical gyres, so we can look at that. So notice right in the north, they're going counterclockwise, so probably some of those wind effects if we remember. So in those higher latitudes, and see where's our subpolar gyre. So it's going clockwise then in the southern hemisphere.
You can kind of see the currents that lead into the middle, right?
And
So like for like the Norwegian one, so you can see like the North Atlantic current kind of.
oh yeah, yeah, and there's, yeah, they're honestly still studying this. So I think I have it somewhere in the notes where they're like studying where does all the water go exactly from the Gulf Stream, because this is like a huge amount of water, and then it all gets, yeah, like diffused, just like you were saying, all over the place.
It almost looks like the North Pacific current moved into the Alaskan current too in a way.
Yeah, exactly. And so that probably influences like the rotation and maybe why it's opposite. Let's look. And so this was an interesting phenomenon that was noticed.
Sorry, can you go back
Oh.
to the subpolar currents? I didn't get the. Thanks, sorry, it's my computer.
Oh, you're fine. So this is an interesting one, and so this is where we see the effects of friction a lot. And so it started with these explorers, Ekman, and they were traveling, and so they noticed, right, that the wind was blowing one direction, but then their ship was traveling almost kind of at a right angle, so either 45 or somewhere between 45 and 90. So they were saying we're almost going, opposite of the wind. So they're going to the right of the wind. And in the southern hemisphere, they move to the left, again, implying our Coriolis effect here again. And so this is, again, where we see friction. And so interestingly, so you would have to test this. So right as you go deeper and deeper down into the ocean, we have more and more friction. And so looking, if we had just an ideal surface current, then traveling with friction, you expect it to go at around a 45-degree angle. And then notice as you go right deeper into the ocean, so that the force of friction, basically, right? So you're traveling, but then you have friction of the water, so it just keeps turning you. And so at certain depths, you could be going at the opposite direction of the wind. So that's pretty fascinating. And then again, right, your Coriolis effect, so that's kind of why it goes in a spiral. So again, that circular pattern. So again, notice, right, it spirals out as you go deeper from that Coriolis effect.
Okay, so the water, because the Coriolis effect is kind of, it's circulating, so that's why things are.
Well, it's the direction that, so it's like your, whatever forces are acting upon you, right? So if you're, so it depends what depth you are. So if you're just at the surface, right, you feel the wind, but then you don't just travel in the direction of the wind, because you have both the Coriolis effect that's spinning you, and also just friction, right? So there's surface friction. And so that's why you expect to travel at like a 45-degree angle. But then as you go deeper, right, there's just physically more like water pushing you kind of the other direction. So you have to think about like your vector forces again being added up, right? So you have like force of wind, right? But then your Coriolis effect is putting you that way, roughly, or spinning. So maybe Coriolis, we should be more spinny effect. And then friction, right, which is going to be working against you or working against you whatever direction you're going. So that's why you get the spiraling effect, is just the deeper you go, right, the more, probably the more friction you have, so then you're going more the opposite direction. Does that?
Like submarines and stuff like that.
Yeah. So that'd be more for, yeah, just like you said, submarines, and then try to figure out your position or which way you need to propel. So that's at least, you know, an interesting observation, and of course you'd probably want to know that if you're trying to sail. And so again, it's just our average then of our friction and our movement. And so they say that we move about 90 degrees to the right then of the wind for the northern hemisphere, and then 90 degrees to the left, our southern hemisphere.
So it'll always be a 90-degree angle to whatever the wind is blowing?
Yeah, roughly. And of course, right, that's just approximately 90, so, you know, getting, depending on,
Give or take.
yeah. Let's see. And so this is just called a geostrophic current. That's just basically from your gravity, and then of course your rotational path. So again, your Coriolis effect. And again, we see this anytime we have our currents piling up. We have, again, just like either a temporary or, you know, from our currents, a point in the sea where it's higher. And so again, that's going to have influence. Everything flows downhill. And so this is just another view of what we were saying, right? That western intensification effect. So your Earth is rotating, again, kind of stretching out these waves. So we got gravity and everything, stretching it out. Coriolis, putting it towards the center. So Coriolis is putting it towards the center. On the western side, they get, again, squished like we saw.
I know that you said that you're going to use more like picture, like stuff for the test, or like as like charting stuff, right? Will you let us know what models potentially would be using come that time, just because there's so many different
Yeah, I will try, like I said,
I know
You
those are the
c-
Geyers.
yeah, like help me, help you. So yeah, I'm thinking, because I would have to give you, I wouldn't expect you to like memorize all these currents, but I might say, you know, like what, yeah, or like what's the western current for the North Pacific Gyre, right? So that could be. So if I said like, what's the western boundary current for the North Pacific subtropical gyre, then you'd have to look, right, and just identify on a map, oh, that's the western one.
So we do need to memorize the current.
No, I would give you the map then with the currents on there. So I'd say like identify.
I would not spell that by myself.
Well,
Oh,
I mean, I wouldn't expect you,
I'll just say K.
yeah. I don't really expect you to memorize any currents, like maybe the Gulf Stream and the California current, but that would probably be more like, what is the warm current, you know, flowing by Florida or whatever. But that's, yeah. I don't want to stress people out, but, so yeah, that's why I'm thinking like map interpretation. All right, so we kind of mentioned this. So again, we had our western intensification. And then eastern boundary currents. Wow, it's already 10:30. Oh, class goes till 11:30. It's like, wow, that is not good. All right, so this is, right, good big picture ideas that we want to take away then. So we know, right, warm ocean currents warm the air at the coast, and they can bring in warm, humid air. And then we also can have cool ocean currents, cool the air. And so what can we say about these currents and maybe how they make certain places more pleasant to live? And we can look at both of these. But they're not too different. So this is August versus February.
And are these numbers on here, degrees in Celsius?
Yep, so they're all Celsius degrees, and so we can appreciate that. So let's just look at August. But what else can we say? Like, what do we notice?
The currents are just recycle themselves.
So currents recycle themselves.
Is moving into the cold, it looks like the warm is moving into the colder one, and it looks like it would just recycle itself.
We can see again, I'll just say like temp circulation or even.
It's important for nutrients and stuff like that in the ocean to.
What else can we say?
I like how it takes the heat from the equator and distributes it. So even though our west coast is colder, it's warmer than it would have been if that heat from the, whatever that K current is, doesn't come over. It's still warming us.
So we have warming effects. So right, we're kind of looking up here, so that could have some warming effects. Where else is the warming noticeable? Thinking of a certain region that's always named.
Like the Pacific Ocean.
I was thinking of another area that's has a mild climate and a lot of people there, relatively speaking.
There's a lot of people you said that live there, is that what you're saying?
At least relatively speaking, and that they shouldn't live there given their latitude.
Are you talking about that big red spot to the left? Is that what you're talking about, like the countries right?
No, although this is a good area. So we should actually mention this region. So, right, it looks super nice and warm. And, man, I forget how many people live here. I would have to look at the stat. But, like, there's a very large majority of the population of the world that lives all in this region. And so there's a lot of reasons for that. So you're pointing out, like, yeah, it's very warm, so that makes it very good farming conditions. And then there's also lots of rivers in that area, so it's very nutrient rich. It's also on the Ring of Fire, so the soil there right, is super new, and it has all the fresh nutrients. So yeah, this is a great place to live, but that actually wasn't the part that I was referring to, but it is excellent for other regions. Yeah, so let's look at, well, look at the Atlantic though. So you got to appreciate, so this is where I was saying, look at our latitudes, because up here, so I was looking at Europe is what I was referring to. So Europe should not be as temperate as it is, right? So if we look on the map, so looking at its latitude, it's like the same as Canada, right? So it's the same level as Canada, but it's not as cold as Canada because we have that Gulf Stream coming in, and obviously, right, it does get diffused, but we're looking at, so we can just compare, so this is 15 to 20 in this light yellowish coloring, and so that brings it to around the same region as, Oregon, California, all the way in those high latitudes. So that makes it, right, very favorable. That's why they have Mediterranean-like seasons over there, right, very nice, very mild, good growing. England, of course, has very mild climates, again, relatively speaking, compared to that latitude. So give the currents a lot of credit for that. Let's see, other. Any other things we want to say? I was trying to find. Okay, this is at least kind of interesting. Going back to what we were saying, that region is super warm. And so again, this is just population density now. So we can see, right, this area has a lot of people in it. And all of that is just due to nice, mild conditions, good growing. Yes, they do have a lot of rain from the monsoon, which we talk about in that chapter, but those monsoons keep it very fertile. So again, a ton of people living there. It's always good to look at the geography and appreciate that. And of course, we have our poles are fairly cold, all that. And again, in February, right, not much difference, so I wish we could look at both these maps a little better. But not too much difference, so a little warm over here in our southern hemisphere, right, as they get the summer, but overall heat in the center and going out like you guys are noticing. All right, so with that, let's talk about upwelling and downwelling. So upwelling is good, so that's just vertical movement of cold, nutrient-rich water. So anytime you have currents, again, diverging, so the equator is a good example of that. So if you have water going away, then that means, right, new water is going to come up and kind of replace that. And this is good, so any place where you have upwelling, you have good biological productivity, so, right, a lot of algae means a lot of other fish. And then, of course, there's also oxygen rich. And so we mentioned that basic principle. So again, cold water dissolves more oxygen or whatever gas, so that's CO2 or oxygen. So more gases come up from the deep ocean and, of course, bring oxygen back up and help renew the oxygen for all the organisms. And so downwelling is going to have the opposite effect then. So this is vertical movement of surface water down. So this can be, right, where currents meet. You can have the downwelling. So, right, if you have a bunch of currents, somebody has to go down. And areas of downwelling, though, are usually more poor biologically speaking. Right, so there's going to be less nutrients as they're kind of being taken away, and so less activity there.
Are there downwelling, so the nutrients kind of just settle to the surface and stay there for the most part? Or wait, not to the surface, to the.
Yeah, I think they'll be more like pushed down, because usually the downwelling, right, you have currents meeting, so then it's kind of forcing the colder waters too, because they're also like cooling, so then they'll go back down. And so like I mentioned, anytime you have diverging surface water, that's going to lead to conditions for upwelling. And again, at the current, there's a lot of upwelling, a lot of high productivities, so that's also why the equator is a good source of life and fish and everything there. So the upwelling has a big effect. And so like we mentioned, converging surface water, now we're going to have low biological productivity. And so this is going to be, let's go back to our currents. And so now where we have converging currents, so notice, right, your Labrador meets up with your Gulf Stream here. So this could be an area where we could have, right, converging, so we're going to have down swelling here in this area. And this could be, you know, something else I ask is like if I refer to the map and if you look at like where the Labrador and Gulf Stream meet, would you expect upswelling or downswelling? Like that might be a question we could ask. So just so you can look at the currents and interpret what's going on.
So the downswelling is as the Atlantic, North Atlantic is moving, the Labrador is going under it, being driven down.
Yeah, well, it's kind of, so they changed the name here because it's right where your Gulf Stream and your Labrador current kind of meet, and then they probably make this new North Atlantic current just from the name. But yeah, exactly where they're meeting, right? So if you have a bunch of water meeting together, there's a lot of volume, so yeah, that's going to force somebody downward, so right there.
So even the Atlantic water moves downward?
Yeah, so as long as it's all a cycle, right? So because the Gulf Stream starts off hot, but then if it meets up with the Labrador current too, which is colder, right, that's going to drive cold water down deeper. And
What causes the upwelling?
so upwelling is going to be like around our equatorial. And so let's find, so anywhere where they're splitting apart, so anywhere around the equator.
Where they're just going in opposite directions, basically.
Yeah, I was trying to find a better, because you have this countercurrent, but probably this countercurrent has to deal with upwelling as well, I would suspect. Because yeah, if you have, right, again, your equatorial is going up down here, your south is going down, so that means right at the equator, there's going to be upwelling. Right, because just,
I can't picture that in my head, because if you have water moving away.
yeah,
how
so
does
it's
that
moving.
heat or rise?
Well, the water, right, so warm water is moving out and moving away, and then so that means, right, more water is going to come back up to kind of take its place as it's moving out.
Kind of hold it in a way.
Yeah. So let's see, so where were we?
This is when they need it to push it.
Yeah. Let's see. So we're looking at that. And so we can also have local coastal upwelling or coastal downwelling effects. And so let's look at this. So if we have upwelling, so upwelling means it's going to come up, bring nutrients to the surface, and then the flow is going to be away from our shore. And so this is the northern hemisphere. And so again, right, it's going to bring cool, nutrient-rich, deep waters up. And so we can see this right on the western side of the U.S. You're going to have coastal upwelling.
So does that mean that on the coast, the tide basically goes against the flow of the water?
Yeah, so it should be going like out, because it's going like up and around and then back out. So bringing, because you're thinking of like which way nutrients are going to, essentially. Because with our upwelling, right, it's bringing stuff from the deep sea to our shores here. And I think we'll see that kind of reflected in our coastal field trip, hopefully, right? There'll be lots of life there. I was looking for Guinevere since she went, but I don't see her. But, right, she said there's a lot of life and a lot of sea stars when she went, so I'm hoping we'll see, again, lots of activity, but, right, we expect these areas to be rich since there's lots of nutrients, so they can support a lot of life, so we can see that. So that's cool. And so coastal downwelling is now the opposite, so now water kind of piles up and then moves downward. And so if you have a downwelling current, it brings nutrients away then. So now it's washing kind of away, so notice, right, it goes down deep. And of course your wind, so your wind is also driving this, so notice with the upwelling, right, wind is flowing away, so going from the surface to the land, and that causes this upwelling, versus the downwelling, where the wind is going from the land, or the water to the land, and so that's helping drive that downwelling. So you kind of see that motion there. So looking at the wind, so again, wind taking our upwelling, so that's favorable, versus wind flowing sea to land, or downswelling.
Can you go back up to the downwelling real quick?
And so you kind of touched on this with like the sea features, but of course that's going to be another influence of upwelling or downwelling, is if you run into like, a table mount or a mountain underneath the ocean, right, that's going to obviously change the flow. So yeah, we looked at this, so right, other causes, just wind, seafloor obstruction, so all that, any sort of geometry change. Again, you guys are getting the big picture, I think. You have to know the topography. And then if there's no, right, ocean layers, and that can also cause more upwelling, where we saw that there was less gradient. So that means, right, our high latitude tends to have more upwelling. And so this is kind of cool. So now we're looking at these currents here. So let's kind of zoom in. And so we have this Antarctic circumpolar current, or your west wind drift, which we can go back to this big picture. So now we're looking at this west wind drift here. And so what's really cool about this current is it's the only current that completely encircles the Earth, so it's able to go all the way around. So now we're looking at it, right? So this is our south pole here, and so it can go all the way around, so we can see that. And so that's kind of fascinating. So of course, right, there's a lack of landmass here, so hence why the current can go all the way. And it is squeezed in here by this Drake Passage, so this area right on the tip of South America and Antarctica that causes some squeezing on our.
Really rough waters right there at the Drake Passage.
Oh, yeah.
I've seen like videos of people that were like taking Antarctic cruises and stuff like that, that were just like, there's super high wind.
Oh,
high
that's
waves
kind
in
of
the Drake
scary.
Passage, Yeah.
So, yeah, I mean, you're hearing the effects, right? So that small passage, so there's going to be more winds, and I'm sure the current gets pretty fast there. Let's see if it. And it also talks about the winds there, which you were alluding to. So your book calls them the screaming 60s for your 60s, the furious 50s for where's our 50? Can't read anymore. So our 50s somewhere in here, and roaring 40s. So yeah, screaming winds. And let's see, what else do we want to look at? So we also have our subtropical convergence, so where waters are coming together. And then we also have, so we looked at our west wind drift. And where's our, so we also have our Antarctic divergence here. So that's another area. So this is where this creates a boundary. And then, so this is really rich. So if you have, right, your divergence, so now thinking about back to upswelling, downswelling. So if it's diverting here, this creates upwelling. And so this area tends to be nutrient rich there. So that helps drive all that. And so, right, you expect marine life here. Let's see, what else do we want to say? And let's see, we should. And then, so, right, your Antarctic convergence over here, that's going to have the opposite effect. So that's going to be more down swelling where they're meeting. And so that's going to be a little poorer there. Let's see, so blah, we mentioned that. So Antarctic convergence, so cold waters meaning your warmer waters. And then again, your divergence, abundant marine life. I'll just star that, as again, we might want to identify places of abundant marine life just based upon our currents. All right, so now let's see, let's look at our North Atlantic subtropical gyre in more detail. And so there's a lot of motion going on here. So it's well studied. So we have our Gulf Stream. So of course that runs along the coast of Florida. But then what's also interesting, right, is all these little areas of circular motion. And so let's also not forget our Sargasso Sea. So again, this boundary is just made from all these currents here. Let's see, what else do we want to say? I thought there was a better picture. I wanted to. This is a picture that I was looking for. So this is kind of interesting because this, I think we've been touching on this, but we're kind of seeing not only the flow, but then just our areas, right, of warm water, and then we have these cool water centers, which is kind of interesting as well. So this is a good picture of it. And so this is really interesting. Again, they're trying to figure out, well, where exactly does all the water go from the Gulf Stream? And so, right, you've already identified that things get interesting up here. And so a lot of you guys have already said, well, the Gulf Stream kind of follows along this path. Obviously, we have, right, the Labrador current coming in, so mixing cold waters. But then they're still studying it, right, and trying to figure out, well, where does all that volume go? Some of y'all pointed out it looks like it probably influences our subpolar gyre up here. And then obviously some of it is carried back down in our Canary current. And so it's just kind of fascinating looking at this map then, because, right, you can see how it's really warm, and then it starts kind of tailing out and spinning off. And what's also interesting is with these meandering patterns, it points out that you have what's called either warm core or cold core rings, or these eddies, as they call them. And so again, that's just a little area where you have some circular rotation. And so here, right, we can see our cold eddies. So I'm pointing them out on both maps, versus kind of your warm ring eddies too. And so you can find, right, different wildlife localized in that area. And it said that some of these eddies could exist for like, 2 years, and then they might flow and move and change. But so there's kind of static. So that's kind of interesting. All right, so let's and again, looking at the detail map of this is just telling us how complex all these currents are. Again, you have surface ones, you have deeper ones, so they're all happening at different levels too. And, right, you can again appreciate this Gulf Stream. So some of it looks like it spirals out and hangs out over here. Some of it probably continues over on the Canary current. And then again, with how this is drawn, we can see that western intensification effect, right? So looking at all these lines, they're very close together too. You can see that, versus over here, they're kind of more spread out and diffuse from, again, your Coriolis effect and everything. All right, and again, so we have our main currents, but it has lots of loops, lots of complexities. So all this is still difficult to be studied and is still studied. All right, so now we're looking at more detail at our South Atlantic subtropical gyre. And so again, we mentioned we have the Brazil current over here. And that was our western current. Right, our eastern one was this Benguela that I can barely pronounce. Blah, warm core rings. Oh. We probably should have said something more about our South Atlantic area. And so what do we remember? Do we remember anything about our South Atlantic area? Which area was really rich in food production because of this? Anybody remember? Yeah, although I think we should be looking at the Pacific Ocean.
I was gonna say, is it like over by the Horn of Africa? That's pretty rich with marine life.
So we'll add, right, rich here. We probably need to look at a better map for what I'm getting at. Yeah, let's look at another map. Because this is the one I was looking for. What do you know about Peru that your book mentions? So you said this was pretty rich too?
Yeah.
Yeah, so all this is known to be pretty rich. So I mentioned anchovies were a big product of Peru. So that means, right, this cold current is probably bringing up nutrients. So this is a good productive current going along there. So it was our wrong side of South America. Let's see. Let's go back. I guess there's not too much to be said here. Just right, your southern boundary is here, the Antarctic. So we mentioned the Gulf Stream, blah, blah, blah. Mentioned these rings, which again is interesting. And so we're missing our Gulf Coast expert today. But, right, the Gulf Coast has kind of similar effect. So our warm ocean and our Gulf Coast, right, we get little loops here. So you have little warm loop eddies. And so right in the Gulf Coast, hurricanes tend to usually gain strength as they pass over these warm waters, especially the warm cores. And of course, I think we know, right, all this area is very hurricane prone, but also at the coast as well, if those hurricanes, right, make it up the East Coast like we saw with Sandy. Let's see. So we've already kind of talked about the Labrador current. Again, I don't want to make anyone memorize currents. And so again, right, the climate effects of this is that it makes everything kind of nice and pleasant and cools things down, so kind of equilibrates our temperatures. So like we mentioned, so the Gulf Stream also warms up our East Coast and then heads all the way up to Northern Europe. And right, the North Atlantic and Norwegian ones also warm Northwestern Europe, so we could go back to this map. So there's our Norwegian current up there, so notice, right, warm. And then any south-moving currents, so those are going to cool. And so such as the Labrador or Canary, so again, going back. So our Labrador, right, that's a cooling current. We, of course, have our California current that keeps us nice and cool here. And what was the other current? What? Oh, Canary. I was like, I blanked out. Yeah, so our Canary, there it is, cooling. And so now it mentions, right, the Indian Ocean circulation. So this is a little bit more complex since you have these monsoons that bring your winds back and forth. So you have this reversal of winds, and so that is a huge influence of our climate. And so let's see. So let's look at this map. And so the monsoons affects, of course, right, our currents. So that's also going to bring an influence on phytoplankton. So again, comparing the productivity. So now let's look. So now we have during the winter monsoon season. So there's going to be a lack of upwelling in these currents. And so now comparatively speaking, so we'd want a high red concentration. And so now looking, right, so there's less productivity in the winter monsoon. And then the summer monsoon, so now you have your wind reversals, so now strong winds generate upwelling again. So you get your nutrient-rich waters. And so you see that reflected here now and off the coast of India as well. So you see a lot of high productivity in that area. And so let's see. Now let's look at our wind patterns. So now we're comparing winter versus summer. And so we can see, right, the currents change. And so let's look in the summer. They're doing more of this clockwise motion. And versus the winter. So the winter time, right, it's almost going the opposite way, so going away from it. And you can see, right, a lot of that is influenced by these winds. And so notice, right, the winds are blowing kind of from the land to the sea. And so that actually changes our direction of our currents. Trying to zoom out a hair so we can see what's going on. So with the monsoon winds, so right there's our north equatorial current. So going along, so it's again completely changing directions versus the summertime where the wind is going from the ocean to the land. And so now that creates a better circular pattern and probably bringing more of this right from our Western Australian back and incorporating that versus the Western Australian here kind of goes away versus bringing those rich nutrients to our landmass there.
What causes that change?
So it's all the monsoon winds here. So yeah, so it's just the temperature. So it's overall, right, if, so water has a higher heat capacity. And so in the winter, right, we have our high cold winds going from the land out towards the sea. So that completely has the winds going in one direction, right? But then in the summer, now it's hot. So now it's the opposite effect. So again, high heat capacity. This land heats up a lot quicker versus the water, right? So the land heats up a lot quicker in the summer. And so now that heat air is going to rise. So that creates low pressure. So now the winds get reversed, basically.
I'm just wondering, since the Atlantic and Pacific don't seem to do this, is that because for the Atlantic, the currents help Europe to be more temperate, so it's not as cold wind, or?
I think it's just the effect, because the Indian Ocean is more trapped here by more landmass. And because it's really this region that gets the monsoon seasons. And so, right, again, it's like with the heat capacity of the land, so we have a lot of land, and so, right, it has lower heat capacity, so the land fluctuates more in temperature versus the ocean. And so then that leads to the overall change. Yeah, and this is, you know, just what it's known for, that monsoon season. And, you know, so you can really also get an effect for how that changes the currents, which is pretty fascinating. Blah, blah, blah. So, and again, right, lots of rain then, of course, in this region, but that makes it very fertile and supports a very large population. And so again, this is just currents that make up our Indian Ocean. And so we could look right at our map. So we have our Somali current here. And let's see, are these on our big map? Oh, there's that one. And this one is on the other side, the Luan current. And yeah, where's our Australian current? Oh, there it is, Australian current. And so again, this is just listing all the little currents that make up these gyres, but, you know, these would be questions that I would probably give on a map, like, oh, which one of these is part of the North Pacific, but I would give you a map to reference. Like, again, I would not make you memorize all these currents, just, can you read a current map? Can you find them? Can you, you might identify, right, which one's warm, which one's cold, but all this would be given to you. Let's see. Blah, blah, blah. So we've already kind of seen that. Again, the Pacific Ocean has 2 large gyres. And so then we can look at this phenomenon called the Walker circulation cell. So this is just a region where you have air pressure across our Pacific equatorial is higher in our eastern Pacific, so this just leads to strong southeast trade winds and a Pacific warm pool. And so I was teasing that earlier, where it also leads to upwelling off the coast of Peru. And so here's our Walker circulation cell. So along the equator, so this is just warming and driving that. So again, right, low pressure created from evaporation, and then any cooling, so cooler water gives that high pressure, so fast moving. And then so under our thermocline layer, then we have upwelling from the cold water, bringing it along that coast there. Oh, sorry. You're welcome. And so again, the effects of this, so warm, and so it's going to be rainy over here on these islands, again contributing to good fertile grounds, and then tends to be clear weather conditions on this side of our Pacific over towards South America. And again, Peru benefits from the upwelling then. All right, so then we can talk about El Nino and La Nina. And so this is, right, big phenomenons in the Pacific Ocean. And so basically, right, this Walker cell then gets disrupted for El Nino. And so that leads to weaker trade winds. And then so that your warm pool migrates eastward. So then, right, that just tells you, okay, this warm water spreads out more across the ocean during El Nino. And so let's look at, yes, this is what I wanted to look at next. So again, right, orient yourself. So there's the islands, and so look at the anomalous warming. And so you have to look at the graph. So it's comparing anomaly, right? So of course this area is probably still warm. It's just its usual temperature. But what we care about is this El Nino effect spreads and warms the water all the way over here, and even, right, the difference is as high as 4 degrees Celsius, so that's kind of cool. And where am I going here? And so back to El Nino. So this means that the thermocline then would be deeper. So, right, if more warm water is coming, then your thermocline is pushed deeper. And so this can lead to more downwelling then as your warm water, right, spreads over here. So that kind of disrupts that upwelling. And so that can create problems for Peru. So, and they would notice that in their like fish activities. So that's why I brought it back to the anchovies. So then years where you have this El Nino effect, you're going to have, your fishing will suffer, and they notice that, which is less food. Oh, sorry, I'm all over the place. Am I scrolling? And I'll post these notes after class. I owe you notes still from Tuesday, so I'll try to get those up. So you have these slides. So and so then we also have, so this is of course all abnormal conditions. So then La Nina is the exact opposite now. So now it's the cool phase. So now you're going to have increased pressure difference across our equatorial. So increased pressure means stronger trade winds, and you may have stronger upwelling then, so with those wind effects, so that's going to drive that upwelling. And so with that, right, a shallow thermocline, cooler than normal seawater, and that would be good for your fishermen. So they would have higher biological productivity, so more fish there. I'll give people a second, copy notes before I scroll around looking for La Nina. So right, this is La Nina conditions, so notice the cold water is kind of spreading out. Notice that thermocline gets smaller. And so of course the map that we want to see is this map. So again, showing the cooling effects. Again, comparing the average temperature anomaly. And so appreciate, right, this big cold region going out.
I don't see much of a difference between the La Nina and the normal condition chart. What would be the differences there?
So let's, are you looking at, so let's, which graph are you looking at, first of all? Is it this one?
Yeah, I see that one, and then I see the normal conditions one as well. And it just looks so similar, I just can't quite tell the difference between the two.
I mean, it is pretty subtle. I was trying to see if I had the
I think
same.
it was all the way up, like, well before the
Look on page 230, that helps. They're both side by side.
Yeah, okay. Oh, here's normal conditions. So it is pretty subtle.
Looks like the upwelling, the La Nina conditions increase in to, like, a little bit further away from the shore than it does in normal conditions.
Yeah.
More cold water into that area.
Yeah, it's pretty subtle. So I pulled up the normal conditions on here. So you can kind of look, right, cold water, you're also trying to appreciate how fat the thermocline is. But then if you go down, right, to La Nina, so notice that cold water is spread just a little bit further out, right? And then your warm water, there's almost no more warm water over here. It's just more upwelling. So, yeah, it's
Is that
subtle.
really the true difference is the extra upwelling?
Yeah, so again, right, extra upwelling from more wind, so more vigorous wind means that it's driving that upwelling more. Yeah, so pushing it so it spreads more. And again, it's kind of subtle on these maps. And that's why, you know, maybe this one's better so you can tell, right, the cold water difference from normal. with La Nina, and then we can go back, so look back at El Nino, so going back to this graph for a second, so right, this warm water has spread all the way. This one is almost showing like no upwelling, so that's, and then your thermocline, right, so now your warm water layer is a lot thicker in El Nino, and that pushes your cold water a lot deeper, so it's more difficult to get that upwelling. And again, look at this chart, right, with the graph and your difference. In El Nino conditions, that red is really spread out versus, again, La Nina, where it's cooling. And so, of course, I mean, I feel like this is a summary of every scientist. They try to predict these weather cycles, but obviously they're hard to predict. And so they say that they have an El Nino warm phase about every 2 to 10 years, highly irregular, and these phases last 12 to 18 months, and they have sediment record of these events, so it's been happening for a while. And they said that they could be part of this specific decadal oscillation cycle. I didn't dive too much into this, but again, that's the difficulty of studying the Earth, so trying to figure out what exact cycle's going on. Maybe there's some overall bigger trend going with just the ocean temperatures that lead to these conditions. And so this oscillation effects last 20 to 30 years. So again, trying to figure out how does this all model together is extremely difficult. Well, because it's talking about different things. So, right, the El Nino phase lasts every 12 to 18 months, but it's saying that it might be part of some big cycle. Yeah, so it's talking about two different things essentially. So that's, again, why it's hard to map these. If you're looking at a cycle, you know, that's going up and down, let's just say for simplicity's sake, right, every 20 to 30 years, but then you have another cycle, you know, oscillating by, you know, 2 to 10, lasting 12 to 18, right? That's like within another cycle. So it's a lot of effects, right? And that's always why it's hard to predict. And so this is just a recording from 1950 to, looks like about, doesn't even say, 2020 roughly, 2019. And so, right, you can just appreciate the oscillation of this. And let's see, standardized departure, I assume this is, it doesn't say whether this is, I assume this is water temperature. But I kind of wish they had a better, trying to see what that graph was supposed to be.
Is it a satellite-derived sea surface temperature anomalies? Like in the other picture?
That's what I'm hoping. I'm pretty sure that's what they're trying to graph. Yeah, it was the temperature anomalies. It's just, I wish they had said this, that this was like degrees Celsius, to be sure.
Now, this might be a silly question. I've noticed over this term so far in this class, they give out some really wacky time frame. So like this one was, we expect to have one every 2 to 10 years. That seems like a really terrible number. Like that seems like something, if I paid to have something funded, I'd be like, what? That's just stupid. Or like that one where like the magnetic poles were changing, it's like every 5,000, every billion years. It was like some radical number. It's like, well, I could have just guessed that. So like, I mean, it's not very, I understand it's hard to get very precise numbers, but that's a very strange number every 2 to 10 years. I mean, that's leaving so much room for error in like these studies and stuff. And I guess I just don't understand. Any other industry, that'd be a no-go. Like, well, no, I know it's hard to do that, but it's like, that just makes it seem so arbitrary.
I mean, honestly, I kind of agree with you, but that's also, I mean, that's
Like,
the hard.
like our study was inconclusive, not, oh, we figured every 2 to 10 years. Like, that's stupid, though.
If you look on the map though, sometimes it happens like every other year, and then there's like a part where it goes almost 5 years without happening. 5 years of like fluctuations of the El Nino, and then there's a drop of the La Nina or whatever.
But I feel like those are like the exceptions, not the rules. And maybe that's just me looking at it not in a scientific way, but like, I don't know, I feel like I'd want something more concrete if I was in, spend, some of these studies, I think you showed that the price tag was like $150,000 just for the survey. So, I don't know.
I mean,
I guess it just seems weird, like, I understand they're hard to do. But
Yeah.
Is that a pretty standard, like, something, it just feels arbitrary to me. I'm not a scientist, I'm an artist, so.
yeah.
It just,
Well, I mean, that's why I honestly struggle with this course, teaching it as a scientist. So I think the problem is we don't know all the effects of the system. And like she was saying, right, all they kind of roughly did is you can average out however long these patterns are. And they say, oh, it's 2 to 10 years, right? So at least it's not on the scale of 100 years, I guess. So yeah, it doesn't feel very precise. So I totally agree with you. Because I'm coming from the chemist mindset, but what I've kind of realized is the chemist is very different in that we look at an isolated system, right? So we get rid of all the noise, and then we literally start reacting, two things together to create one. And even that, it's really hard to study. Like, I understand where you're coming from. So then it's like, in oceanography, how the heck do we study everything? Because, yeah, we're talking about the wind, the Coriolis effect, the friction, then other weather patterns, global weather patterns, and we don't even understand, like, a lot of the Earth, really. Like, I feel like if there's anything you should take away, it's like we still have so much to research, right? Because we don't know what drives a lot of these big currents.
There's volcanoes and stuff like that too. There's such a big, like, room for error of how much, like.
Yeah.
well, you may as well just, I guess my thing would just be like, we just don't know instead of, because I think I saw another one, it was like every 2 to 100 years, and I was like, that's so wide, like.
Statistics like that, like, too, unfortunately.
Yeah, I mean, that's really the difficulty of studying, our Earth, and everything's on this ridiculous time scale. And I mean, I agree with you.
Oh, no, I'm not trying to argue, it just feels like some of these numbers they throw out are just so arbitrary, and it feels like a waste of money at that point.
And those are other, like,
But,
that's another discussion that I think is totally valid, and the population is not allowed to participate in, which was kind of bothersome with research funding, because there is huge questions of, like, you only have so much money. Technically, it's taxpayer money that is going to fund, right, the NSF and all these research things. So why doesn't the taxpayer have more of a say? And, those are all, that gets into just how the scientific system is set up, how research is done, unfortunately. And, and then obviously the physical limitations of just like studying the ocean. But
like I said, it's just silly. If I were to go back to a client, I'd be like, yeah, it's gonna be between like, $2 and $100 for this logo. They'd be like, well, that's huge. Like,
yeah,
there's the middle ground. I mean,
yeah.
it's just, like I said, just from an outsider, not as a scientist, it just seems weird to me. That's all. I'll keep my mouth shut now.
No, you're allowed to criticize. I think that's the problem, is the citizen does, and now I'm like ready to go on a rant, but it's like,
Sorry.
no, because a lot of people have this elitist mentality, and I hate it. Like, speaking as a person who got your PhD, like, you're not special, right? But people have this like real elitist mentality of like the public doesn't know how to look at the data, and that's always like a huge issue, and they always want to put barriers to the public, and I think it's
Yeah, they want you to
unfortunate.
submit to authority on a subject, and I have 2 brain cells that can rub together to read a book. So.
Exactly, yeah, and and it's that's part of this class is like, yeah, like you can criticize a study, like I encourage you to, and like say that maybe it's not worth billions of dollars, and that is like another existential question is like, are we doing the right thing for humanity by funding all these projects? And you could say that with any sort of research, right? Like, again, I take it back to my PhD personally, like, did I really accomplish anything? I don't know. Me, I learned a lot personally, but did I go save the earth? No, I didn't. Could that money have been put towards something else? Like, maybe. But those are all big bigger philosophical
Philosophical
questions,
questions.
yeah.
When you talk about the money being put towards something else, it just makes me think of, did you guys hear about the UN decision recently where America voted that food is not a human right, but everybody else voted it is?
Yeah,
Yeah.
that's, yeah, I
Money
mean,
towards food.
right, it's like, maybe we should solve our fundamental issues of homeless and food shortages first before we go try to study El
Yeah, how
Nino.
things work.
Yeah, and then we get inconclusive results. Like, you have a point. I totally agree. Like, but that's where the elite people will come in and try to tell you, no, you're too stupid to understand science, or like anyone who says like the science is settled and can't be debated, like don't trust that person. Like science is literally up for debate. Like that is the point of science. If it can't stand rigorous questioning, then something's wrong. Like that's where scientific method comes into play. It's never just, we're done, Again, I take it back to germ theory. Germ theory is still a theory. Even though I feel like we proved it, right? We can isolate what we believe is the bacteria or viruses that cause our illness. We still should keep an open mind in case evidence presents itself to the contrary.
That seems reasonable.
Yeah, should be, but yeah. What you got into, right? People just want to control or make money and blah, blah, blah. Anyways, I think that's a good place to stop. So we go more into blah, blah, blah. Yeah, we kind of skipped over currents. But we could talk about this on Tuesday. All right, let's take a 10-minute break. We'll migrate to lab. Excellent questions, though.